SQL. Wait, no, sorry, wrong one. SQL is a language you should have used at least once. After all, it's the native language for relational databases with over 50 years of incremental improvements and standardization behind it. But you probably have never used it to its full potential because it's just a very different programming paradigm from normal languages. Before I truly learned SQL, I mostly wrote my queries like this. And you probably do too. It makes sense, most of us just build basic CRUD apps. But what do you do when you have a more advanced use case, where you actually need some insight from your data? Then this primitive and inefficient usage of SQL and by extension databases become problematic. It doesn't allow you to take advantage of the more advanced and powerful optimizations that databases can perform. Let's use an investment bank for an example. We want to find the average number of trades and the average return per week per industry sector. So we have a trades table containing the date and time of the trade, the return and the industry sector. Most people would probably start out with the following. Select the average return, count and sector grouping by week of the trade and the sector. Then in your endpoint you take this and calculate the average per sector in code by using three maps. One for the count of weeks, one for the number of trades, and one for the sum of returns per sector. Then just use the maps to compute the average. This might be intuitive, but it can get very inefficient. What if we only want to include trades with a higher than the overall average return? Doing it this way, we need to select all data and compute it in the server. This means we're going to send the entire database over the network to our server, which has two big issues. We use a lot of I/O, which is one of the big costs of databases, either in monetary terms, if you're using the cloud, or performance being dragged down. And all the data might not fit in memory on the server. Generally, the database has more compute than memory. Even at just a billion trades, you are out of memory. So we can't do that. Maybe we instead decide to use two select queries. One to find the average and then one select with a very close filtering trades by the average. Not very nice, latency suffers from the two serial queries and it also has a data consistency problem. The average we use to filter is not the actual average when we filter. There are no guarantees that it's reading data from the same point in time. But we can actually solve this completely using standard SQL. So let's start out with the simple case, the average of the weekly trades per sector. What we're actually doing is called a multi-level aggregation. The only way to compute that in SQL is by using something called CTEs, common table expressions. They give you a way to define temporary results you can use during the execution of the query. And the syntax is really similar to normal queries. You simply write with weekly averages as, and then the previous query we had before. And now we can use weekly averages in our actual select query. The final select is what the query actually returns when you run it, which is exactly the average of the weekly trades per sector. For the more complex case, we somehow need to include only trades that have a greater return than the average return in weekly averages. And we can do that in two ways, with one being a crazy CTE-based cross-join. First, compute the average we're filtering by. This will clearly return a single value. Then just do a select trades, filter averages. This does a cross-join, which is a very dangerous operation unless you know what you're doing. Every row in table A is copied to be joined with every row in table B, resulting in the size of the table to become size of A times size of B. Of course, for us, table B is size 1, so the resulting size is the same as trades, but if we had two rows, the resulting size would be 2 times trades, so we very quickly grow the data size. Don't use it unless you are extremely careful. After we do the cross-join, we just filter with a var clause to check that return is greater than the average return and then use this table in the weekly averages. But that's clearly crazy. We can do this much simpler by using a subquery. They allow, among other things, where clauses to depend on other select queries. So let's use the trades table for weekly averages again, insert a where clause, checking that return is greater than the select average return from trades. So this way we don't need that interesting cross-join stuff. And now this select will only include trades with returns greater than the average return. Now, what if trades are in different currencies? With that assumption, the query is clearly incorrect. If someone made a trade in Zimbabwean dollars, the average will be kicked to the moon and no trades in US dollars would count even if their return is actually much larger in real terms. So we need to convert the currency. If the trade is not in US dollars, we should convert it using the current currency exchange rate. This clearly requires calling an external API to get the rate. So now the query is hopelessly broken because we can't call external APIs from SQL, right? Well, not exactly. We can actually do it using probably the most powerful and unknown feature in SQL, something called a UDF, a user-defined function. If you have seen a UDF before, you have probably seen the query language function subclass of them, where you only use SQL, create your function, say what it returns, and do some select depending on the parameter to the function and return your value. But in Postgres, you can also write and execute raw C functions. If you're doing something very computationally expensive, this is probably what you will use. We won't be though, because REST API requests are not computationally expensive. They just take time of waiting for the network. Instead, we will use a third option, Python. It's surprisingly easy to use actually. We don't even need to leave SQL. Just create the replace function, convert currency, take the amount, the from currency and the to currency as parameters, then return a numeric and set the language to PL Python 2U. So we're using Python 2. You can also use Python 3 if you want to, but I'm lazy. Then just import requests and JSON, try doing a request to the API using the URL, encoding the parameters in the request. Then you serialize the response JSON, multiplying the amount by the currency conversion, and return the converted amount. Then we just call this function in weekly trades before the aggregation function call, easy. Now the query works again. But beware, this comes with a bunch of caveats. It's so bad, in fact, that you should probably avoid doing it this way, unless absolutely required. For example, if DNS resolution is slow, the API server is slow, or just about anything else in between the database and the server is broken, the database session will hang and just completely take down our entire system, and it would be extremely difficult to debug. Also in this case, we're sending a lot of API requests, 2 for each row in the trades table. So what you should probably instead do for this particular case is just do currency conversion at insertion time into trades. But I couldn't come up with a better example for UDFs, so sorry about that. Anyway, it should be enough of an example. Generally, I imagine you'll probably only do this for really computationally expensive operations. What we have done is pushed our aggregation code into the database. Now you might argue that this doesn't really matter in your normal request response workflows, and I kind of agree. You shouldn't ever put this kind of aggregation in a critical path where you need interactive latency. It should be pre-computed. But it does start mattering for doing the pre-computation, and generally for doing large-scale data analytics processing. If we don't do this, the unaggregated data we get when not using CTEs and sub-expressions probably wouldn't fit on a server, and we would need to write specific and complex business logic to make the analytics work. Just imagine if we have billions of trades, which is probably doable with just a few tens of thousands of portfolios. It just doesn't scale in any easy way. Sure, you can figure it out manually, but why? If you use CTEs, the underlying SQL executor, like a Postgres, Spark or Flink cluster, can just optimize the execution out to multiple servers and do this query efficiently and fast. And that's why SQL is more than just select star. Please like and subscribe, and thank you for watching.